This video will discuss the subject of resonance, how amplitude can be increased with a small force, and we'll talk about waves and superposition and interference. So you're familiar with the playground illustration where a person sits on a swing and the parent pushes each time the child gets back towards the parent in the arc of the motion. As the swinging stops for an instant, parent pushes forward and the amplitude builds up for the person swinging. That's the concept of resonance. We have an applied force that has a frequency equal to the natural frequency for the system. And that natural frequency for something like a spring, the period for a spring in simple harmonic motion is 2 pi times the square root of m over k. The frequency is just 1 over the period, so we would have a natural frequency of 1 over 2 pi square root of k over m. So we have a natural frequency for systems that oscillate, and if we apply a force with the same frequency as the natural frequency, we can build up a resonance effect, increase the amplitude. It's also possible to apply the force at other frequencies that are smaller than the natural frequency of the system by a factor of 2 or a factor of 4. Take your pick. So in the playground illustration, we'd push once every 2 swings or once every 4 swings. But the base case is the small force is applied with a frequency equal to the natural frequency of the system. So this can be a problem with earthquakes. The earthquake wave, as it shakes the ground, as the wave comes across where the building is, if the natural frequency of back and forth motion for the top of the building is the same as the frequency of the earthquakes, then that earthquake gives a little push to the building in such a way every cycle of the swaying of the building. Earthquake delivers some energy that builds up the amplitude of the sway, and the building can fall down. We can show how energy can move from one system to another with this illustration of resonance. If we would create some sound that is the exact frequency of one of the strings of this piano, then that string of the piano will start vibrating. We'll pick up that tone. Another illustration here, if we have an object that's going up and down, and each time the object is starting to come up, we again pull up with our finger, we'll build up the amplitude of the motion. If we lift our finger up and down very rapidly, not equal to the frequency of the motion, then the amplitude will not build up, because part of the time we'll be pulling up when the ball is going down, and that would take energy away from the oscillation. But if we lift our finger at the frequency equal to the natural frequency of the system, then when the ball is going up, we pull our finger up, we increase the energy in the system. The next cycle, when the ball is going up, we lift our finger up, that'll increase the energy in the system, and the amplitude will increase. That's the principle of resonance. And if we have some damping in the situation, that can minimize the amplitude. But if there's not much damping, then we can build up a large amplitude. So I'm not a structural engineer, but I believe that buildings have methods in them, bracing in them, to limit the amplitude. And they have other equipment as well to compensate for the swaying, to limit the amount of swaying. But if damping is present, then you can limit the amplitude. You should go to YouTube and watch a video on the Tacoma Narrows Bridge. As wind came across here, the wind caused a resonance in the system, and the amplitude built up, and the bridge fell down. So write down some questions for your instructor, but we're going to go on to the next topic, which is waves. And a wave is a repeated oscillation that has some amplitude, has a wavelength between 2 successive waves. From peak to peak would be a wavelength, or from valley to valley would be a wavelength. The interesting for all types of waves, there's a relationship between the speed of the wavelength, and the frequency of the wave. And the speed of the wave is equal to wavelength times frequency. So we have water waves, we have waves on ropes, we have sound waves, we have light waves. Wave phenomenon is common. So we get a little time to spend on it in this chapter. Two types of waves, two categories. If the wave involves an oscillation perpendicular to the velocity of the wave, then we have a transverse wave. And for the case of a rope, we shake the rope up and down. The particles of the rope are vibrating up and down while the wave goes forward. That would be a transverse wave. Light also is a transverse wave, but it has no medium that is required for light to travel to one place to another. That's something that sets light apart from other waves. For a wave on a rope, you need a rope. For water waves, you need water. For sound waves, you need air or liquid or solid for the energy to propagate through. But for light, it goes on its own. It's self-propagating. It does not need a medium to travel through. But it is a transverse wave. There's a model for light that says it's composed of oscillating electric and magnetic fields that are perpendicular to each other and perpendicular to the velocity of the wave. Longitudinal waves are like sound. In the longitudinal situation, the medium is vibrating parallel to the velocity of the wave. So the molecules go back and forth, not up and down, but back and forth along the direction of the wave velocity. And water waves, you have a mixture. If you have a cork on a body of water and a wave comes by, it does go up and down. That's a big part of its motion, but it also goes back and forth a little bit. So it's a combination of transverse and longitudinal waves. Here's a transverse wave. A person is shaking one end of a coil of wire, like a slinky, and we see the oscillation up and down. The velocity is to the right. So this fits the category of transverse wave. The medium here is vibrating perpendicular to the direction of the velocity. If here we have a slinky and the coils of wire here, we push in on them and create a high pressure situation. This is like sound. We create high pressure, and that high pressure will be passed from coil to coil, and the wave will travel on down the slinky. So those are our characteristics, transverse and longitudinal waves, that you should understand how it works. So here's a seagull, and the wave is going by. The seagull's going to go up and down. The seagull's all going to go left and right a little bit. But again, wavelength, the lambda symbol stands for wavelength, peak to peak, or valley to valley, or midway up the wave to the next midway up the wave where we're going up. Any two similar successive points can be used to calculate the wavelength. Most often we'll go from peak to peak. That distance in meters is the wavelength. Guitar, got an amplifier with a vibrating paper cone here for the speaker, and we get sound waves. The waves carry energy. Waves carry energy and can make a piece of paper vibrate, make your eardrum vibrate so your brain can detect the sound. So superposition, the concept of superposition. Suppose we have two waves traveling in the same medium. Here there are two sources of water waves, and one of them is coming this way, another is coming across off to the lower right. And when they cross each other's position, the amplitudes add up. This is the principle of superposition. As long as we're not going past some elastic limit on the ability of the medium to move, then the net amplitude is the sum of the individual amplitudes at that point at a particular time. The principle of superposition. We add up the separate amplitudes of the waves. So if we have wave 1 and wave 2, at a particular point, wave 1 has an amplitude of 5 centimeters, wave 2 has an amplitude of 7 centimeters. The net amplitude would be 12 centimeters. The amplitudes add 5 centimeters plus 12 centimeters. We get 12 centimeters for the amplitude. This is interference, and there are two forms of interference. When I was talking about the peak of wave 1 and the peak of wave 2 being at the same place at the same time, then we have what's called constructive interference. The amplitude is going to increase. Let's talk about a different wave. Let's suppose wave 1 has an amplitude of 5 centimeters, wave 2 has an amplitude of 5 centimeters. But now we consider the case where the peak of wave 1 and the valley of wave 2 are present at the same point at the same time. This will be a displacement of plus 5 centimeters from wave 1, a displacement of minus 5 centimeters for wave 2 to the valley. 5 plus or minus 5 is 0, and we'll get destructive interference when we have two waves present with a peak of one wave and a valley of the other wave present. It may be partially destructive, or if it's a full peak and a full valley and they're the same magnitude quantities, 5 centimeters up to the peak, minus 5 centimeters down to the valley. If they're that same magnitude, then our net is 0, and we get destructive interference. We see no evidence of the wave. So a drawing of this with constructive interference. These two valleys are adding up, these two peaks are adding up, and we're getting a larger amplitude. Here's destructive interference. These waves are out of phase by half a wavelength. So when we have a peak for wave 1, we have a valley for wave 2. That's half wavelength downstream. And here's valley for wave 1, peak for wave 2. Again, we get 0. All along here, this is the net of two waves adding together, destructive interference. Here we have a combination of two waves, wave 1 with a certain frequency, wave 2 with a different frequency. And if we add these two together, the largest effect is the effect of wave 1 taking us up and taking us down. But wave 2 modulates the net result and gives us this squiggly pattern. But superposition, adding up the displacements of the two waves. So, the situation of a standing wave, when we have one wave traveling to the left, another wave traveling to the right, we can get a situation where at one time the two peaks line up, the valleys line up, and we get a big amplitude. As the motion continues a little bit, we're getting the valley of wave 1 at the same place as the peak of wave 2, and if these waves have the same amplitude, that adds to 0. Here, peak for wave 1, valley for wave 2, add to 0. Then the waves move a little bit further, and we get full amplitude again, and in between these there's going to be partial cancellation of the two waves. But we get a standing wave here, and if this is occurring on a rope or an air column, you can definitely detect that a standing wave is present. The standing wave looks as if it's not moving. If you have a vibrating rope or guitar string or piano string, piano wire, if you can observe it oscillate, what you'll find is that it just kind of stands there. Even though the waves are traveling left and right, the net gives us an effect as if the medium is pulled off to the side permanently. We see what's called a standing wave. With the sound in an air column, this will produce a loud sound if we have a standing wave in our situation. So here's a drawing of what's occurring here. We have a wave, one traveling to the left, one traveling to the right, and we can get these nodes and antinodes where we have destructive interference at the node, constructive interference at the antinode. There is 1/2 wavelength from a node to a node, a full wavelength all the way out to the right in here. So if we have a string that's anchored on this wall, the two ends are shown here, that would be length L. A half wavelength would be equal to L. In finding the frequency here, this is really the wave velocity equals frequency times wavelength. And then we solve for frequency. The frequency times wavelength, the wavelength is equal to 2L. That is achieved because half of a wavelength is the node-to-node distance, L, in this diagram. Half of a wavelength is node to node. So the wavelength would be 2 times L, and frequency times wavelength is our velocity for the wave. So the wave velocity divided by 2L, that gives us the frequency. This would be called the fundamental frequency. It's the lowest frequency. It's the fundamental frequency. There are also harmonics, upper frequency numbers. You could call it the overtone, but most people would call this the second harmonic. And this would be the third harmonic with a factor of 2 multiplying the fundamental frequency. I would call this the second harmonic, this one the third harmonic. This is a tone that's higher than the fundamental. It's higher by a factor of 2 in its frequency. If the fundamental frequency was 60 hertz, this overtone would have a frequency of 120 hertz. This one would have 180 hertz, 3 times 60. So we can get these standing waves set up in a string here between 2 walls, and the different wavelengths create different frequencies for standing waves. But nodes where we have destructive interference, antinode where we get the full range of motion of the medium. And you can work this out as far as, lambda over 2 is equal to L here, and in this situation we have a second frequency here that is higher. We're getting more oscillations in this space of the length L. And over here, more oscillations in the space of this length L. So perhaps your instructor will do some examples of this on the board. I will be doing so for my students. Then the concept of beats. This is a method for tuning an orchestra or a band. We have some instrument that is the standard, the chair or the violins, and we'll play with practice, play a standard note. The other instruments will tune to eliminate what are called beats. If we have 2 waves here that are slightly different frequencies, here they're starting in phase and we have constructive interference, but the frequencies are slightly different. There'll come a time when we'll have destructive interference, and then a little bit later they'll be back to constructive, and you'll hear a beating of loudness of the sound. So that's a good way to tune the instruments. When you get rid of the beats, when there's no longer this kind of warbling wow, 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 of the sound, then the 2 frequencies are the same and the instruments are in tune. That's what you want for your orchestra. When everybody is playing A, you want everyone to have the same frequency for the sound that they generate. Photograph of earthquake damage here. Again, setting up a resonance. The earthquake can set up a resonance with the natural frequency of the building and cause damage. A seismometer to record the strength of earthquake waves. And an illustration here of the constructive interference. We have 2 sources of a wave. The lines here are drawn, the solid line at the high pressure of the sound wave, what we call the peak. So here we have a peak, and we get a loud sound. And there can be places in a room that are set up, a room is set up, where you get cancellation of the 2 waves. You get kind of a dead spot in the room where we have destructive interference occurring, where the peak of one wave is at the same place as the valley of another wave. So that's where we're going to end here. It's the concept of resonance, applying a small force at a frequency equal to the natural frequency of the system. We can build up a large amplitude. The concept of waves, we have transverse waves where the medium oscillates perpendicular to the velocity, longitudinal waves where the medium is oscillating parallel to the velocity. We have superposition. We add up the separate displacements of the 2 waves to get the net displacement. And we can have constructive interference and destructive interference. Constructive if we have peak and peak at the same point at the same time. And destructive interference, we have the peak of one wave and the valley of another wave. And then all waves obey the speed of the wave is equal to wavelength times frequency. So keep practicing with that and ask your instructor some questions. That's where we're going to end this particular video.